Why are blue elliptical galaxies smaller and in less dense regions of the universe?
This data shows that, while blue elliptical galaxies have most of their light enclosed within a radius 5,000 light-years smaller than the average elliptical, they still have close to the same mass. This suggests that blue ellipticals are composed of a relatively small number of stars that are high mass, which would allow the galaxies to be smaller, but still have about the same mass as normal ellipticals.
These scatter plots show the mass versus the radius of the blue ellipticals and all ellipticals. This supports the data shown in the previous chart, showing a small difference in the mass, but a more significant difference in the radius. Once again, it suggests that blue ellipticals are composed of a relatively small number of stars that are high mass, allowing them to be smaller, but still have the same mass as normal elliptical galaxies.
This chart shows the average local density of various types of galaxies, that is, how many galaxies are close by. Larger numbers mean more galaxies are close by, smaller numbers means less galaxies are close by. This information shows that both red ellipticals and red spirals are in more dense areas than average elliptical or spirals. Both blue ellipticals and blue spirals are in less dense areas than the average elliptical or spiral. Therefore, red galaxies are found in more dense areas, and blue galaxies are found in less dense areas. This suggests that galaxies located in less dense areas tend to have more high-mass blue stars, since there is less gravitational interference from other galaxies to prevent higher-mass stars from forming.
Here are shown two galaxies from the Galaxy Zoo data, one red elliptical and one blue elliptical. These galaxies have similar masses, however, the blue galaxy has a much smaller radius than the red galaxy. The local density of the blue galaxy is much lower than that of the red galaxy.
Our hypothesis was that blue ellipticals are smaller and in less dense regions of the universe because they can only form in less dense regions, where there is less gravitational interference from other galaxies, allowing high-mass stars to form more easily. We also thought that because of this, though the galaxies would have similar mass to other ellipticals, they would be smaller because they would have less stars, since the stars would be more massive, so each star would contain a larger percentage of the galaxy's mass.
The evidence in the charts and graphs shown previously support this hypothesis and seem to confirm that blue ellipticals can only form in less dense regions and are composed mainly of high-mass stars, causing the galaxies to be smaller.
A couple assumptions made here are that the galaxies were sorted into the correct types, and that the data on each galaxy is accurate. An inaccuracy in any of the data would result in different average values for the characteristics of the galaxies. Though a few small inaccuracies would not affect the conclusion reached from the data, many large inaccuracies could potentially suggest that the hypothesis is wrong.
Though the conclusions reached from the data appear to have answered the original question, there are other questions such as, if we studied the elliptical more closely, would we find that there are in fact composed of mainly high-mass blue stars? And what is the ultimate fate of blue elliptical galaxies? Will they remain more isolated, or will they move toward more dense regions of the universe as they age?
Though data can be used to answer questions and confirm hypotheses, finding an answer to one question only poses further questions and prompts a more in-depth analysis. The more we know in science, the more we realize we don't know. Science is like the universe. It is expanding at an increasing rate.